Guys, today we're going to talk about IP routing, configuration of the routers. The process of forwarding IP packets across the entire network, as you can see from the subnet /24, another subnet which are divided by the first router. You go to the second and the third router now, and we go to each other subnet. We have done some different approaches there. We have used some virtual LAN, some virtual ports, as you can see. So let's configure them step by step. First of all, we have to host the forward IP packets to the default router or to the gateway. In this case, my IP address and mask is 172.16.1.9/24. My local subnet contains number from 172.16.1.0 and 72.16.1.255. It will include the subnet ID and broadcast address. Destination address is 172.16.2.9. It is not my local subnet, as you can see. It will send a packet to my default gateway, which is set up to 172.16.1.1 now. To send the packet encapsulating them from the other encapsulation, your virtual local ports, and to send it to the other address, which is the host A default gateway. But the second step is to decide whether to process the incoming frame. The router uses data link trailers FCC's field to check the frame if any error has occurred during transmission. If there will be any error of the frame, it will be discarded now. The router also checks destination data link addresses to decide whether the frame is intended to. As you can see for illustration, the first router, and to check the FCC with the frame is unchanged. You can see from the encapsulation ATH and the IP packet, and this the MAC address with the hexadecimal. We check for the port. Is this port the MAC address? And it checks there. If it is, then it will send the packets there. And the third step is the encapsulation of the IP packets. You can see this is done from the end user now. It gets the IP and packets from the first router. It changes the IPs, and now ports. Now we have the ETH label. The next step is to forward the packet. The router now has the list of all other 5 routes. The network have the 5 subnets. The first router has a route for each of the 5 subnets. When matching IP packet destination with the routing table, the router looks the packets at destination IP address, which is 172.16.2.9, and will compare it with the other range addresses which you define by each subnet. The next step is encapsulation of the IP packets in a new frame, and the 6th step is transmitting the new frame. As you can see from illustration, we have some matching subnet and forwarding hop. This is the first router. What happens? The port GigaInt bit Ethernet 00 and serial in the next right side we have serial 000, serial 001. As you see in the subnet, where they go to the next hop. Now, if you'd like to dump some command line interface, just a configuration of the router interface, we have network A, B. Of course, we will divide now 2 switches and 2 hosts. They're going to be a different network. The A network is 1.0 and the B network is 1.128. But the main network is 1.0. So let's go configure it. We enable it. Conf-ter, configure terminal. We access the port with the interface gap internet 000. We put an IP address, the common IP address. Of course, it will be 1.1 if you want. We can put the subnet mask /25, which is 255.255.255.128. We put the description if you want, and no shot to turn on the port. Now let's exit from this interface. Let's go to the other interface. In IP Internet 001, please put there an address, as you can see. One more now, 1.29. Description if you want. Now let's turn it out or turn it on, and let's save it. Do copy and start. Now we have to verify the interface configuration and connectivity. To list it, the interface status, we have some different protocols such as show interface brief, show protocol, and show IP interface with type number. Interface status codes. For example, if we have line status in the first status code, it will mean that the first layer status. It will check the right or wrong cable device and the power on. We have protocol status, which if it happens in the second status code, it refers to the layer 2 status. It will be always down and the line status is down now. If the line status is up, the protocol status of down is usually caused by mismatched data link layer configuration. If we have administratively down and protocol status is down, the interface shutdown command configured on it. If we have down, the interface is not shut down, but the physical layer is a problem with it. For example, no cable has been attached, or the interface is broken, or the internet to the switch interface or the other cable is shut down. If we are up, down, almost always refer to the data link layer problem. This is open with the configurations. Serial links have this combination when one router was configured with point-to-point protocol, and the other defaults use HDLC. If we have up and up, layer 1 and layer 2 the interface are always functioning. This is some router packet forwarding decision, a simple illustration. We have two routers with a directly connected network. The first router has three directly connected networks, 10.0, 11.0, and 209.165.200.224. The first router has two remote network. You can access it and learn more about the second router, which is 1.0 and 2.0. We have another illustration. This is done some show IP routes command to show the routing table where we access these IP networks. This is a simple illustration. First router and the second router are directly connected to the network, but we can access them now with some labels such as ABC. It will identify the network it was done by the router, define destination network, and now it is connected. Now identify the interface on the router connected to the destination network. We have remote network and routing tables. Don't worry about this one, but just have more illustrations about this. Let's see. The first one, identify the network was done by the router. B, identifies the destination network. C, identifies the massive distance and trustworthiness of the router source. In the end of this, I will tell you about this one. Identifies the materials to reach the remote network. Identifies the next hop IP address to reach the remote network. Identifies the amount of elapsed time since the network was discovered. Identifies the outgoing interface on the router to reach the destination network. Now, as I said, for the trustworthiness, it used the greedy algorithm. If you have learned from the lecture I've posted on YouTube, I've done some calculation there and introduced some algorithms about greedy algorithms such as Castra, Bellman Ford, which is really useful to find the next hop with the computer networks. So don't forget to check them out if you don't understand it now. Don't forget to check that, because it will be really worth it for us today and in the future. For instance, we have some common codes for direct connected remote networks. We have L, identify the network assigned to router interface. It will allow the router to efficiently determine whether it receives a packet for the interface instead of being forwarded. C. Identify the right connected network. S. Identify the right route was manually created by an administrator to reach specific network. And this is mainly known as static route. D. Identify the route was learned dynamically from another router using AIGRP routing protocol. The O. Identifies the route was learned dynamically from another route using OSPF routing protocol. R. Identifies the route was learned dynamically from another router using RIP routing protocol. But we have some distance in there from administrative and metric. Is the first criterion that the router uses to determine which routing protocol to use, and if two protocols provide route information for the same destination. Administrative distance is a measure of trustworthiness of the source of the routing information. Administrative distance has only local significance and is not advertised in routing tab date. Now the metric, if the router learns two different paths from the same network from the same routing protocol, it will decide which route is better and will be placed in the routing table. Now the metric is the measure used to decide which route is better. We use a grid algorithm, so always the lower number is better and faster. Each routing protocol uses its own metric. So RIP uses the hop count as metric, IRP uses the bandwidth and delay, while OSPF uses the cost. As you can see, we have some default distance values with the route source. Connect interface is 0, static route is 1, ARGP is 5, BGP 20, internal IRGP is 20, IGRP is 100, OSPF 110, is 115, RIP is 120, HGP is 140, ODR 160, external IGP 170, internal BGP 200, and if we don't know, it is 255, which is the lowest one. We don't want that one. We have some table entries. The first router uses the RIP to each host. Because the RIP uses the hop count, this is measured. The path through router 2 will be used to reach the 10.0 subnet. This is because the subnet is only one router away on the path. The other path will have a higher measure of 2 because the subnet is 2 routers away. There will be disadvantages, as you can see from the lines. If the first path through the second router was 500 CCK modem link, while the other path, the 3 and 4, is high-speed wide area network link. The first router will still choose the path through R2 as the best route because RIP uses only a hop count as its metric. As you can see, this is the next hop address. This is dumps out routing tables. Starting routing. A network router is a device that is used to route traffic. Routers forward packets by learning about remote networks and maintaining routing information. To forward packets correctly, a router needs some basic information about the network and the packet to be forwarded. Static routing, path identification and selection. To identify the sources of route information, determine from which sources other routers are, then they can learn the path to given destination. Identify routes, determine the initial possible routes or paths to the intended destination. Select routes, select the best path to the intended destination. Maintain and verify route information, determine whether the known paths to destination are most current. And packet forwarding, identify destination address, determine destination or the IP address of the packet that needs to be routed. We have some branches now. Path identification and selection discovers possible routes to the intended destination, selects the best route, maintains and verifies the route information, and packet forwarding routing defines the packet destination. Static routing and the differences between dynamic. Static network administrator, it will enter manually IP addresses. The topology will require manual update to the route, and behavior can be precisely controlled. A dynamic is changed dynamically and will adjust it by our needs. The topology you can learn and maintain routes to the remote destination by exchanging routing updates. It discovers new networks by sharing routing table information. But when to use it? We of course don't forget static routes. We always use in small networks that require simple routing in a hub and spoke network topology when we want to create a quick and ad hoc route. Of course, we don't want static routing in a large network, and the network is expected to scale as we don't want to put all the IPs there one by one, and we have to change it every time we have to scale it up. This is an configuration of static routing. We have configured unidirectional static routes to and from a stub network to allow communication to occur. Static routing configuration is we define a path to destination. As you can see from the IP address and subnets, it will use the IP address to NAS hub router, or sometimes it use the outbound interface of the local router. Now the default routes. The subnetwork to reach all that network beyond the first A router. It's a simple illustration, check that out. We have three networks which are now on the class visualization with a serial 000 and connected directly to the connected network. And now dynamic routing protocols. It are sets of processes, algorithms, and messages that are used to exchange route information. After the already connected routes have been installed, a router populates its routing table with its best path to remote destinations as chosen by the routing protocol. After the path is always determined, a router can route to the learned networks. Dynamic routing protocol do as follows. They discover networks, maintain up-to-date route information, and choose always the best path destination network because they are dynamic. And find a new best path if the current path is no longer available. You have interior-exterior routing protocols, characteristic of an autonomous system, and AS is the collection of networks with a common administrative domain. IGPs operate within an administrative S. EGPs connect with different autonomous systems, as you can see from the illustration. But now let's have some distance vector protocols. They use distance to determine the best path on network remotely. They are measured in hops. Through distance metric, it could be delayed or lost sometimes. The distance metric is hop, then each time the packet goes through a router, a hop is considered to have traversed. The protocol will compute by the routing table to each other next neighbor. They use the Bellman-Ford algorithm to calculate the best routes, as I said in the beginning. Compared with the link state routing protocols, distance vector protocols are simple to configure and require little management now. But sometimes they are susceptible to routing loops and converge slower than link state route protocols. Distance vector protocols also use more bandwidth because they send complete routing table, while link state protocols send specific updates only when topology changes occur. We have RIP and IGP, which are some examples of distance vector routing protocols. Link state protocols. Unlike distance vector protocols, link state protocols don't advertise through entire routing table. They advertise information about the network topology. So in the end, all the routers running a link state protocols have the same topology database. They cover much faster distance than routing protocols. They support cluster routing. They send updates using multicast address and use triggered routing updates. They still require more router CPU and memory usage than the distance vector and can be hard to configure. Each router running a link state routing protocols create three different tables. The first one is neighbor. The table of neighbor routers running the same link state routing protocols. The topology table, the table that stores the topology of the entire network. Routing table, the table that stores the best routes. OSPF shortest path algorithm, use calculate OSPF, and is our example of link state routing protocols. Here the distance vector. You will send the entire routing table and link states, slow coverage, routing loops, updates, network topology not known, simply, and RIP and RGP. We have link state information, yes, fast coverage, yes, less susceptible, multicast, okay, multi-tier network, yes, can be hard to configure, example, SPF is easy. So thank you for sticking by to the end of me. Don't forget the algorithm and all topologies we learned today. Some OSPF, IRGP, distances, connected, RIP. And if you have any question, please write me down below.